I'd like to thank Ali for inviting me to this wonderful symposium. So the fact that you can actually enjoy the beautiful San Diego weather and come to this symposium, part is because you can see this beautiful scenery. And I'm an ophthalmologist, a physician scientist. So what I want to do today is to use eye as a not only window to the soul, or actually the window to the systemic and also eye diseases as an example how we apply powerful genomics and also artificial intelligence technology to improve the healthcare. So just to quickly orient you with the eyes, and so the light transmitting through the cornea, the lens, and then focus on retina. Retina is this exquisite neural tissue, and macular is where the cones are, and then cones are the ones that is involving subserving central vision, precision vision, and what you actually using this now. And the rods are the light you use for light vision, and then you have macular here, which has concentrated cones, and you have optic nerve, which is transmitting the axons to the brain. And this part is actually affected by glaucoma, very common disease, and macular degeneration. Diabetic retinopathy are the ones actually affecting retina. One other feature I want to point out to you is retina has exquisite vasculature. That vasculature is actually similar to brain and also heart and also neural tissue and systemic circulations. So this is actually also a very, very powerful and also easy way to assess the cardiovascular disease. And this you are only seeing the we call the first and secondary tertiary blood vessels. Underneath is actually millions of actually capillary bed, which can be easily imaged using non-invasive apparatus such as optical coherence tomography and phenotyped. So with that as an introduction, I want to move into the first part of the talk is you have heard wonderful talks about identifying genetic mutations. So the next step, obviously, is how we can use this information to impart on treatment strategies. So I want to use this example of a sort of rare disease, which is actually genotype, but it's actually collectively is actually very common genetic disease, blinding disease called retinitis pigmentosa. So this is actually a disease specifically affected the rods, the ones that are affecting the light vision. And this is a typical example how you see them. So the feature is actually has 60 plus different genes, over 100,000 mutations. So it is very, very hard to actually using your traditional gene therapy approach. So you have heard probably the first actually FDA-approved gene therapy is for this blinding condition called Leber's congenital amaurosis. Unfortunately, this is actually a disease only have about 500 patients in the United States, and because Sparks that who actually initially used this actually gene therapy approach to treat this disease had to actually gone through extensive drug development. So the price tag for each patient is actually near $1 million per patient. So obviously for disease that is such as RP that have so many different genes and mutations, this is not a feasible approach for every single gene. So what should we do with this actually situation? So what we actually propose to do is a in vivo in situ cellular reprogramming strategy where we want to switch adjacent similar cells to the different cell phase. In this case, first of all, we like to switch rods to cone, and in this case, because rods is a mutation specific or honorable population of cells, and if we switch to the cones, you switch the context of mutation. In this case, the rod-specific gene mutation will not affect the cone development or functions, so essentially you rescue the phenotype function. We can do this because the controlling of the rod-cone cell phase binary switch is by this gene called NRL or NR2E3. So by inactivating this gene, you should be able to easily switch rods to cone. In addition, we have 200 million rods, we only have 5 million cones, so it's easy to switch 5 million rods to cone and then I rescue the function of the visual function. So this is actually one strategy we're using. And second strategy is outlined here is that if you depleted all the rods in the end stage of RP patients, you also have another lineage of cell called myeloglial cells. Those are glial cells that is actually in a differential development pathway, end-stage differentiation pathway that's still there. So you can impart another strategy, which is just to switch the glial cell lineage to the neuronal cell lineage. From there, you switch them from the rods to cone lineage to completely rescue the phenotype. And this is actually obviously a potentially general strategy to treat other diseases such as Parkinson's, Alzheimer's disease. So I don't have to give you an introduction for CRISPR technology. And so in order to do this, we actually have developed in collaboration with Juan Carlos Belmonte's group of some of the technologies that can trace and also doing gene editing in using homology-independent pathway. I won't go into detail. Suffice to say, we're able to actually rescue and also in animal model rescue the phenotype. What I want to do is actually tell you that a further improvement of this technology, which is gene and mutation-independent pathway, which is switching the rods to cone. And again, so we're able to use this strategy using AAV virus with injection to the subretinal space and switch the cone to rods. And what we have shown in this paper is we were able to switch in several hundreds of thousands of rods to cone, and that actually is sufficient to rescue vision as shown by electrophysiology, by visual function, and also by histology. And this is just one of the examples that this reprogramming strategy was part of the report by CBS 60 Minutes, along with Feng Zhang and Eric Lander and Mitch Toft's group. And shown here is mouse, which is actually putting this test called optical kinetics testing, where we can actually precisely measure the vision of the mouse and by rotating this drum. And what we'll show here is we can dramatically improve the mouse vision. So this is actually an example of how we can actually impart using a different reprogramming strategy in combination with cellular reprogramming CRISPR technology to improve vision. So I'm actually going to switch gears, tell you more about how do we use big data and artificial intelligence to improve health care. And so this is actually a review we wrote, and you have heard so much about AI, its applications. So what we envision is actually right now we're mostly are in this corner here doing a lot of diagnostics. We're hoping that a lot of actually strategies and applications can be used to impart on how do we actually prescribe drugs, how do we actually monitor longitudinally the patient disease progressions. Obviously, you have heard a lot about how to use AI to monitor in the health populations, and it's actually impact. And we haven't actually talked about a lot of regulations and the big data we can use to monitor the epidemic strategies or events. And I will talk a little bit about how do we actually create a patient-centric electromedical record system which patient can carry around and also to use for their management. I'll start with how to apply image data to the AI diagnostic strategies. So since I'm a retinal specialist, actually one of the technology I use a lot is called optical coherence tomography. This is a very essential diagnosis that is used by 70 million times, probably one of the most commonly used ophthalmic diagnostic tools for us to diagnose macular degeneration, diabetic retinopathy, and glaucoma. So here is one of the papers we published early on. And the reason I want to show you this is actually we use AI to actually form this cell cover image, which contains 40,000 optical coherence tomography images. So if you look actually carefully, those are small images from them. And anyway, so this is the technology being most commonly used in eye clinic. And for 40 seconds scan, we were able to obtain 30,000 scans, build up this non-invasive image. This is actually this example of those images. So this is actually normal retina. You do an optical cross-section of this, and this is actually the fundus photo of this retina. This is early signs of macular degeneration. This is a drusen. There's a deposit underneath the retina. Diabetic retinopathy, which is a lot of bleeding, swelling in the retina. You can see those cheese holes. And this is actually a very common type of macular degeneration called wet macular degeneration. You can see the blood vessel growing underneath the retina. So as you can see, those patterns are very distinct, so should be very amenable to pattern recognition, such as deep learning. So in this case, I would create a convoluted neural network. We use transfer learning. You have heard a lot about this, and in this case, we were able to train from 200,000 OCT images and to classify those diseases: wet macular degeneration, diabetic macular edema, drusen, and normal patients. And so this is actually a comparison of how they do with retina specialists. And if you concentrating on the this corner here, so initially after 2 weeks of the training, and it gets about 88% accuracy, and upon another 2 days of training, it gets about 60%, 5% accuracy. Those are 2 retina fellows in Charlie Eye Institute of UCSD, and those are actually mid-career and senior retinal physicians that is grading the SAM images. As you can see that already by just simply 2 to 3 weeks of training, the AI is actually achieving the retinal specialist level, which requires at least 10 to 20 years of training. So this is actually a very powerful illustration that how the AI can do so well in pattern recognition. You can imagine that by giving 1 million or 1 billion images, it will definitely surpass what we hear and become very, very actually accurate for diagnosing those diseases. Not only you'll be able to diagnose diseases, what we want to also do is telling the AI that they should point out where the lesion is, or where actually they actually assess and make a diagnosis. What we did is actually using this occlusion test to show that what we did is I systematically put a black box around these images to ask the question where, if you block those images, that you'll degrade the accuracy of the diagnosis, and then put a heat map on those. You can see in each case, inevitably, it's actually the lesion that is where actually AI is looking for diagnostic accuracy. So this is actually a way we can now use this to communicate between physician and patients to the AI, so actually to solve the problem of traditionally the black box AI phenomenon. So we were using this to guide our diagnostic and also treatment strategies. I won't go into the detail for this. After transfer learning with the ImageNet, which is just the standard pictures to OCT images in the eye, we also further did a transfer learning of the SAM algorithms to see how well they will do in pediatric patients' chest X-ray for pneumonia. As you know that pneumonia is one of the very common conditions in pediatric population. And not only we need to differentiate pneumonia from normal, we also need to tell whether it's a bacterial pneumonia or viral pneumonia, because bacterial pneumonia need urgent care and institution of the antibiotics treatment, whereas viral pneumonia just need supportive care. So this is actually, again, an example. Just by 5,000 images, we're able to actually achieve 90% accuracy, showing the power of transfer learning and artificial intelligence. I told you about the OCT, and then so we're in the process also using the retina images to diagnose all the diseases. So right now we trained 1 million patients' images using retina images for common diseases: macular degeneration, glaucoma, diabetic retinopathy, cataracts, and also embark on about 1 million diabetic and hypertension, cardiovascular disease patients' images. So we're in the process actually training those images to essentially making a comprehensive diagnostic platform and also put them into iPhone as attachment. So in this case, we can directly deploy to the rural areas of China and India, Brazil, where by 30 seconds, and we'll be able to actually diagnose all those common eye and also systemic diseases, as well as actually, and this is actually a cloud-based service. You can just upload to the cloud, and then within 30 seconds, you can get a diagnosis and use this as triage and treatment platform. That is actually one of the things we're going on. Hopefully, I can give you more further report soon. One of the other issues about using artificial intelligence, particularly in application in medicine, is actually as our physicians, as we do not just only look at the images. We synthesize vast majority of the data, including the electronic medical records. You have heard the two wonderful talks before me about how to utilize those. However, worldwide, if you look at the electronic medical records, it's kind of like a mess, and especially in China, and different vendors, and in this case, different language as compared to English, and is a challenge in terms of unify and harmonize and to apply AI to this. So to address this, we take an approach to look at the 1.3 million pediatric medical records from single medical center in China, and then we first utilized to create a knowledge-based text database or library in which we manually using 50 pediatricians to curate 50,000 records, and then to form the clinical pathway, and then take that and to use deep learning and natural language processing to extract the free text from the electromedical records and form a fully structured database from there using deep learning and the logistic regression to classify the disease. So this is actually a spectrum of disease and in a comprehensive pediatric hospital. And so this is actually some of the examples as how we actually, you can think that the Chinese is even actually worse than English because they write actually the medical records in a continuous sentence without stopping. And then for one word, fever, it's actually two words, and each one of these little two words does not mean anything about fever. So you need to go in segment all the sentences and put out the very important the keywords and then forming the structure of the language. So I tell you here for like 2 minutes, which took us actually 4 years to do. So afterwards, and then so we asked the AI, say, how would you take those keywords and structure the EMR, and then go ahead, just classify them according to your actually thinking. We did not actually tell AI what they should do. And surprisingly, and not surprisingly, they actually also formed the organ-based diagnostic system. So in this case, that obviously for pediatric population, by far the most disease or presentation of cases are in the respiratory disease and there's also others. There's neuropsychiatric, systemic disease, GI and GU, etc. And this condition is highly accurate, and I can show you that for anywhere from 95% to 85% accuracy. And we also was able to compare this to 20 pediatricians, and which they are basically form diagnostic groups. So we use, for each cases, we have 5 physician groups. This is actually a junior group, for which is actually chief residents, and to the junior physician up to 8 years. This is 8 years to 15 years, 15 years to 20 years, and 20, 25 and above. And this is the F score, which this is the AI's performance. This is actually synthetic performance of all the diagnoses. As you can see, AI consistently actually perform better than junior to mid-level physicians, and comparable, slightly worse than the senior physicians. This is actually being trained on 1.5 million electronic medical records. Again, just like OCT, I believe that if we're giving AI 1 billion records, or the diagnostic accuracy going to be much higher and better. Because as a physician, it's impossible for us to memorize and notice, also remember all the details of any single subspecialty. So I put this up as a reminder to segue to the second part of my talking. And then so shortly after our publication of our paper, and there's a New York Times article reporting this. And I want to read to you this sentence here. So each year, millions of Americans walk out of the doctor's office with a misdiagnosis. So millions. So the estimation is actually anywhere from 10% to 20% of the diagnosis were misdiagnosis. That's actually, I mean, I didn't actually know this. This is astounding. Obviously, there's a lot of reasons why this happened. So what we actually now are doing is to not only just continue to build the pediatric diagnostic AI system. Now we have took 3 million adult EMR and then formed the same diagnostic platform. Now we merged the pediatric and adult AI platform to form a comprehensive AI system. So what we're actually doing now are twofold. One is to form an online system that can take patients' chief complaint and then ask series of questions, yes or no question, to map patient's disease to a specific diagnostic codes. So that's actually something we're envisioning to use this system to triage patients in the rural areas of countries such as China or Brazil. If they have a situation, you can imagine in the middle of the night and a mom has a baby with a 99 fever, and then what are you going to do? And the next actually closest clinic is actually 500 miles away. So I think those are going to be very useful tools for the rural for resource poor rural areas to gain actually good medical care. Secondly, we are in the process of also making a physician compatible platform for which we will deploy in the emergency room situation. You probably actually have heard that even in actually the United States, where the care has been so advanced, the average wait for going to ER is 5 hours, and no matter you have whatever trivial flu or actually very serious disease, you're going to be charged for $700. So we're hoping that in this case, and potentially a physician who is actually in the 10th hour of their shift, haven't eaten breakfast, now have actually 5 chest pain and 2 gunshot wounds and 2 motor vehicle accidents. In this situation, I mean, there's a likelihood, realistic likelihood, this physician can potentially miss something which can potentially result into serious complication, possibly mortality or paralysis. And we're hoping that the AI system can spot check physicians, give them actually remind them they need to check this and that, and then make sure they do not miss some of the important diagnoses. So again, so I think there's a lot of applications. The ER, you have heard a lot of exciting talks here, and I just think this is just the beginning of what we can do for our patients and for our systems. I'm hoping, just like Dr. Eric Topo said, within the next 5-10 years, we can actually dramatically help to improve our system, lower the cost, and also make our physicians actually having a lot of more actually time and quality interactions with our patients. With that, I want to thank all my collaborators and my postdoc and students, and be happy to take some questions later.